Okay, the university has asked all professors to announce their exams. I don't know why, because you have all this information on Solus anyway, but here we are. So your exam is 2 Mondays from now. It's at night, it's at Dunning Hall. The exam is already set because it has to go to the printer today. So I do know what's on the exam. I will let you know what's on the exam on Wednesday. And then there will be no class on Thursday, I believe, unless someone wants one for some reason. Please let me know if you want a class on Thursday for some reason, and I will hold the class. Okay, question? What's up?
Oh, I was going to ask what's going to be on the exam.
Yeah, no, I'll let you know on Thursday. I've looked at a bunch of the past exams. The questions on there are reasonable for exam questions. They covered some slightly different stuff than we did, so they're not all applicable. Most of the exam questions are pretty reasonable. I'll give you more details though of what's going to be on the actual exam. Yeah.
I was looking at past exams.
Yeah.
Most of them covered like bash stuff and C stuff.
Yeah.
I think I remember you mentioning we were only going to cover C stuff.
No, primarily C, but there will be some bash because the midterm didn't ask you about looping in bash or any of the string processing stuff. So that's the only thing that'll be on the exam. Well, I shouldn't say that's the only thing. There's like basic shell scripting, getting the command line arguments, basic bash commands, stuff like that might show up as part of a question. Yeah?
Will we have to do handwritten code?
Yeah, you have to. It's all handwritten code, unfortunately, but there's a but. It's not, what's the best way to put it? It's not very, it shouldn't be very complicated code. And there's no, I have to memorize the details of function X or whatever. So I'll give you do get a handout. So there will be a reference handout for you guys that you receive. But there's no memorize what this library function does or how to call this library function or how do I convert a string or a character or a float or something with 3 digits of precision or anything like that. Anything that you could look up, like any basic programming question you can look up is not part of the exam, right? So I don't care if you memorize syntax and stuff like that. Okay, exam processes. So I'm going to try to wrap up the process stuff today. At the end of the last lecture, we talked about orphan and zombie processes, right? So remember, an orphan process occurs when the parent finishes before the child, right? So the parent finishes before the child. The way it works in C, or in Unix, sorry, is that somebody has to look at the return value or the exit status of a child process before the operating system can clean up the ID that was assigned to the process, right? Now, because there's only a finite number of IDs in the OS, it's important that you do this, or that some process cleans up or looks at the return, the exit status. Otherwise, it's possible for the operating system to run out of process IDs. And the actual number of IDs isn't that much. It's not super high. If anybody looked at the fork bomb article I showed you, that also explains why you have to, it's not good to leave orphan processes around, right? Because it occupies up a process ID, and that's a finite resource. Now, if you do orphan a process, the way it works in Linux is it gets adopted by some other process, and then the other process looks at the exit status. So normally orphan processes aren't an issue. Zombie processes are a little worse. So a zombie process occurs when the child process terminates before the parent, and the parent never looks to see what the exit status of the child was. There are programs that spawn many child processes. For good reason, right? Because you need to have a bunch of child processes do work that's independent of one another, right? So in those types of applications, it's important that that the parent look at the exit status of all of its children, right? Otherwise, again, the operating system eventually runs out of process IDs, and then it can't launch any new processes, right? So zombie processes are are a bigger problem. So there's a little program that creates a zombie process. I'm not going to run it again. All right, so the way you get rid of a zombie process. So if you have a parent process that runs a long time and is regularly spawning child processes, right? the parent process needs to look at the exit status of those child processes. Right? And so in Unix, the terminology is that the parent must wait on the child. And all that means is that the parent has to wait for the child process to terminate or stop, at which point the parent process can then look at the exit status or the status of the child. So the term that's used is waiting. Now, there's a bunch of ways you can wait. So strategy number 1. The parent just waits for the child process and does nothing until the child process finishes. Right? So that's called blocking. Right? So in other words, the parent is blocked from doing anything until the child finishes running. Right? If you have a very long running child process, you want to avoid that. Right? Because otherwise the parent's kind of useless. Right? It's just sitting there waiting for the child to finish. That's similar to what happens when you run a bash program. So if you're in bash and you run a long-lived program in the foreground, the terminal is no longer useful to you. Right? So that's another example of a blocked process. Okay, so the other way you can do this is that the parent process can regularly check if the child process has terminated or stopped. So every once in a while, the parent process checks to see if there are any child processes that have stopped or terminated. Right? While it's not checking, the parent process can be doing some extra work. Right? So that's called polling. And then in the third version, you can handle a signal that the operating system gives you when a child terminates or stops. Right? So when a child process terminates or stops, the operating system sends a signal back to the parent process. Right? So for that, we need to learn how to deal with signals. Okay? So while the parent is waiting for a signal to come, it doesn't actually wait, it just runs. So when the signal comes, the parent is interrupted. So whatever the parent was doing stops, and then it tries to handle the incoming signal. So I'll show you how that works today. All right, so if you want to do strategy number 1, so you just want to wait until the child finishes, then you use the function called wait. There's a slightly more complicated version of this function, but for now we'll use wait. Okay, so wait waits for a child process to finish, to terminate. This one won't wait for a child process to stop. Right? It'll wait for it to terminate. If it returns the process ID of the child that has terminated. If there's some sort of error, it returns -1, and then sets no. The exit status of the child is stored in a variable that the parent process passes in. Right? So the parent process makes an int value, passes in the address of that int value. Then the wait function can set the value of that variable, right? Which is why you have to pass in a pointer. This function is defined in the system library called CISC220. Right? So this is the exact same example program as before. So everything's the same up until you get to the parent process part. Right? So up here we're forking a process, and then the child's doing something here. This is where the parent is doing something. Right? So in the parent process, I'm going to print it's waiting for the child, and then there's this wait function right here. Right? So that function blocks. Right? So in other words, the parent just sits here on this line, right, waiting for the child process to finish. Right? When the child process finishes, the parent prints something out, and if it wants to, it can continue doing something else. Right? Like, it could spawn another child, or it could do whatever other work it needs to do. Right? So maybe the child process completed some result, and it now can do something. The parent process can do something with that result. Right? So that wait statement there blocks. So if you run, this is wait. That's not actually wait x1. Sorry. This is it's fork example number 6, I think. I didn't rename it. Sorry. But it's right here. Okay. So here. There's our wait function, right? I'm going to show you this one next, but right here it's going to wait. So what this thing should do is it should launch the child process should run, the parent process should just sit there doing nothing until the child process finishes. So this is number 6, right? So there's the parent, right? It launches the child. The child process is just sleeping for a little while. Right? So there it is, it's going to sleep, then it wakes up, right? I'll run it one more time. Right? So the child process is now running, the parent process is now waiting, right? So nothing's happening. right? The child is doing whatever it's doing. The parent process is stuck waiting for the child. When the child wakes up, it exits, right? And so you can see here that the parent process receives the exit status as 0, right? So apparently the child process exited cleanly, right, with no errors. Okay, so that's the wait function. Now, the wait function actually calls a more complicated version of the function called wait PID. Right? So remember, PID is just the process ID. Right? So the child, wait calls this function with a value. I forget what the value. It's somewhere on the next slide. I'll tell you what the values are. So this is the more general version of the function that you want to use. Right? So waiting on a process will wait on the child process with that ID. It'll store the exit status of the child process in that variable there. And then you can pass it in a bunch of options to control how the waiting is done. Right? It returns the same information as wait. So it returns the ID of the terminated or stopped child in this case. And it'll return -1 if there's some sort of error. Right? Okay, so that's the function. The parameter PID is the process ID of the child to wait for. Right? So the parent process always gets the child process ID, so you can always pass in that value. Now, there are some other choices that you can use. Right? So instead of passing in the process ID of the child, you can pass in the constant called wait any. That's also defined in this header file. Right? So as soon as you include that header file, you get all these constants. Right? So wait any will return the status information about any child. So if your parent process spawns a bunch of children, right, you don't have to wait on any one of their IDs, right? You can wait for, so you can get information for any of the children, right? So you don't have to wait for each one individually. There's another constant called wait my group, which returns the status information about any child in the same process group as the calling process. Now, the process groups are a little bit funny. So we never talked about what a process group is. Right? So when you start a process, so when a parent process starts a child process, the two processes are in what are called the same process group. Right? So if you start a process, the child process gets placed in the same process group as the parent. Right? But there is a way to assign the child process to a different process group. Now that's way beyond the scope of this course. Right? So there's reasons why you want to do this, but they're not really relevant to us right now. Right? There's a lot of this leads into the operating systems course again. Right? When you just use wait, right? Wait calls wait PID with an ID of wait my group. So it'll wait on any child process in the same process group. Now, options is 0, right? So you can pass in no options, which means wait until the child terminates or stops, right? So that's what the plain old wait function uses, right? So it passes in 0 for the option. Or you can use what's called a bitwise OR of one of these three, right? So W no hang means that wait PID returns immediately instead of waiting. Right? So if you call wait PID and there is no child process that has terminated or stopped, wait PID returns immediately. Right? And returns 0, I think. I think it returns 0. Right? So it returns immediately instead of waiting. Right? W untraced will return and report the status of any child process that has been stopped, as well as those that have been terminated. Right? So if you want to find information about stopped processes, you have to pass in W untraced as one of your options. And then W continued returns if a stopped child has been resumed. Right? So remember, you stop a child process from the command line. If you're in bash, you would use Control Z to stop it. Right? And then to resume it again, you either type in FG or BG. Right? So foreground or background to continue the process. Right, so when you type in FG or BG, that sends the SIG continued signal to the child process to continue. Right? So you can check when a child process has stopped or continued using a combination of these two here. Okay, so exact same program again, except this time I'm using wait PID. right? So this is the equivalent of what wait does, right? So if you pass in wait my group and 0 for the option, you get the exact same result as you get by using just wait, right? So in other words, if you comment out this line and uncomment this line and then recompile, you'll get the exact same result as before. There, and then, sorry, there. So it'll do the exact same thing, right? So the parent process starts the child process does something, right? Parent process just waits until the child finishes, and then when the child finishes, it prints out the exit status. Okay, so instead of waiting, right? So instead of just waiting, the parent process waiting around doing nothing, right? You can instead choose to regularly call wait PID in a loop of some kind, right? So you call wait PID in a loop, right? If there's no child process that's terminated or stopped, the parent process goes off and does something else, right? But then it has to come back and check wait PID again, right? So for this, you're going to use the W no hang option, right? So in other words, check to see if there's a child that's stopped or not, that's stopped or terminated. If there isn't, return immediately. Right, so now the structure of your program changes. Right, so normally what happens is you end up in a loop of some kind. So here I've got an infinite loop. Right, so while 1, so while true, right, I'm going to check the exit status, right, of the child process. Right, so I'm looking at, I only have one child, so I know that I can check that ID. Right, I know the ID of the child to check. Right, I'm going to store the exit status in that variable there. Right, I'm going to use W no hang so that this function returns immediately if there's no stopped child process. Right, so if the result is 0, that means that there's no child process that's ready, that's stopped or terminated. So I'm going to call do something. So I'm going to go off and do something. Do something in this case just sleeps for 1 second. So it just, it's just doing, it's doing nothing, but it's just simulating doing something. Right? Now, if the result is equal to the child ID, so that means that child has returned. Right? So it's, it's stopped or terminated. So now you can, now I print out that the child exited with its status, right? And then we break out of this while loop. Right? So presumably what this program is doing is that it's doing something until the child finishes and then it stops, right? That's what that break statement's doing. So when you run this program, let's look at the code quickly. Okay, so do something just prints out that the parent is doing something and then it goes to sleep for 1 second, right? So that simulates doing something, right? Back in the, here's our loop. Right? So inside of our loop, right? Once again, waiting for the child, right? But we don't actually wait, right? If there is no child, we go and do something, right? Otherwise, you print the exit status of the child, and then break out of this loop, right? When you break out of the loop, if you want to, the parent can continue here, right? So let's see. So this one, behaves a little bit differently. Right, so now the child process is sleeping, and now the parent is doing something. Right, every second it comes back and checks if the child process is done. Right, when the child process wakes, right, the parent process prints out that the child process has exited with a status of 0, and then because of the way this code is written, right, it breaks out of the while loop and ends up down here. Right, when you end up down here, you're outside of the while loop, so the program just ends. Right, so you can wait as well. So you can poll, right? So poll any children that are, you poll to check if any children have stopped or terminated. Right. So when you use wait or wait PID in the way that we have so far, right, that relies on the parent testing, right, whether or not the child process is terminated or stopped. Right. Your alternative is to have the operating system signal that a child process has terminated or stopped. Right? So it's the operating system that knows when a process stops. If a child process stops, the operating system sends a signal, that one right there, right, sig child, to the parent whenever when the child process stops, right? So this already happens. The default action of a process receiving sig child is to ignore it, right? So when you look inside this program here, right? There's our do something function. Here's our main function, right? Nowhere in this code or nowhere in this program is there any code that says, hey, if I got this signal called sig child, I have to do something about that, right? So you can put that code in, right? So in other words, you can respond to a signal by handling the signal. Right? So to handle a signal, your program can define what are called signal handlers. Right? And a signal handler is just a function. Right? You use the signal function or the sig action function to direct received signals to the appropriate signal handler. Right? So the idea is you use the signal function and you tell the operating system what should happen when a signal comes in. Right? So you say, call this function when you receive the signal. Right? Now, if you actually do man signal, you'll see this in the documentation. Right? So the signal function is very easy to use, but the man page says that the only portable use of signal is to set the signal's disposition to signal ignore or signal default. Right? So do whatever sig default tells the program to do whatever it would normally do when it receives a particular signal. Signal ignore says ignore the signal completely. It says the semantics when using signal to establish a signal handler vary across systems. So that means it works differently on Windows or Mac or BSD, right, or any other version of Unix. In other words, its behavior is non-standard, right? And it says do not use it for this purpose, right? Unfortunately, it's very easy to use, and on Linux, it behaves in a very particular way. So let's use signal for the time being. Right? Now remember, there's a whole whack of signals that the operating system defines. Right? So every operating system will have a different set of signals. You can list the signals for your OS by doing kill minus L. Right? And on Linux, you get 64 of them. At least on a 64-bit Linux, you get 64. I don't know what you get on a 32-bit Linux. Right? And there's a whole bunch of them. Right? To find out what each signal corresponds to, you can do man signal. Man 7 signal, I think, to get the information for each signal, right? And now remember, we talked about a few of these earlier, right? So the one that we're interested in today is sig child, right? So sig child is sent by the system when a child process terminates or stops. Its default action in the parent process is that the parent ignores the signal, right? So it receives a signal, but nothing happens. Okay, we're going to change the way that behaves. What else? Oh, sig t stop. That's what happens when you type Control Z, right? And then sig int. That's what happens when you press Control C, right? And so notice that the default action for sig int is to terminate the process, right? But you can change that too. So you can put in a signal handler that can handle that signal, and then instead of stopping the program or terminating the program when the user presses Control C, you can do something else. Similarly with sig stop, right? So you can put in a signal handler that responds to the signal, and that will prevent the caller or the user of the program from from stopping your process. Right? And you can install the signal handler for any one of these 64. Yeah, you can install a signal handler for any one of the 64 here. Okay, this is good because this is going to be something like this is going to show up on the exam. Hint, hint. Okay, so the signal header file defines the following type def. Right, so it defines a type. Well, it defines an alias for a type called sig handler _ t. Right, now remember what this thing is. Right, when you write something like this. Right, so sig handler t, that's the name of the type, right? That's the name of the type alias, right? That's a pointer, right? Star. So this is a pointer to a function that returns void and has an int parameter, right? So, sig handler t, pointer to a function that returns void and has one int parameter, right? So that tells you what your signal handler signature has to look like, right? So your signal handlers in your program are going to be methods that look like void, some method name, one int parameter, right? So the parameter is the signal number that's passed to the function, right? So when your signal handler is called, the operating system passes the signal number to the function, right? So these are all, right, dot 1, it corresponds to sig HUP, 2 corresponds to sig int, and so on and so on, right? So you're just getting one of these integer numbers. Right, so here's a generic, oh wait, how long is this one? Right, here's a generic function that that you could use as a signal handler, right? Right, so remember the signal handler returns void, right? Has one int parameter. So return void has one int parameter, right? It doesn't matter what you name it. You give it whatever name you want, right? This particular one is going to try to handle sig int, right? So that's control C, right? And it will try to handle control Z as well, right? So it's going to handle both of these signals. Right? Now notice when you do this, you prevent control C from working and control Z from working if you tell the signal function to catch those functions or to handle those functions, right? And that's not necessarily a good thing because this means that the user of your program cannot stop the program by typing in control C or sending the sig int signal to the program, and they can't stop it or pause it by sending it control Z, right? Or sending the sig stop signal from some other way, right? So this is generally something you don't want to do, right? Okay. Now, before that function actually works, you have to call the signal function, right? So the signal function, you say what signal do you want to handle, right? And which function do you want to handle the signal, right? So the documentation says signal establishes an action, establishes that function as the action for the signal signum, right? And it returns the action previously assigned for this signal, right? So it returns one of these things here. Right? Action can be a function pointer, so I can pass it a pointer to this function, or I can pass it one of these two values, right? And the man page is trying to tell you that you should really only pass it one of these two values, right? In other words, you should not be using it the way I'm about to show you how to use it. Okay? So DFL is the default action assigned to the signal. IGN is ignore, right? Now, it turns out you cannot ignore sig kill or sig stop, right? So you can't ignore all functions, all signals. Right? But you can still handle them. You can't, a process cannot handle sig kill. So sig kill is handled by the operating system. Okay, so in the main method here, right, I've got a comment here. I said don't uncomment both of these lines, right? You got two lines here, right? So I'm going to call signal, and I'm going to pass in sig stop, right? And I'm going to tell it to use my function here to catch the signal, right? So whenever I send it sig stop to that process, the process is not going to stop, right? Instead, the signal comes to the signal handler, right? Here we just print out it detected something and it keeps on going. So the process doesn't actually stop when you run this program. So this is signal 1, right? That's all it is. When I run this program, signal 1. Okay, so nothing happens, right? So nothing happens because there's this infinite loop here, right? While 1, the program goes to sleep for 1 second, right? Now, if I just wait here, nothing's going to happen, right? The program will run forever. So I'd like to stop the program by sending control Z, right? And now you send control Z, and the program prints out that it detected sig stop, but it keeps going, right? So what actually happens here is that while it's sleeping, right, the program receives a signal, and the sleep function is interrupted. Right? So in other words, whatever the sleep function does, it stops doing. And now you jump up to the signal handler. Right? In the signal handler, it detects that it received sig stop, so it prints that back out. Right? When it prints that back out, return comes back to here, but it doesn't go back into the sleep function. or it may not go back into the sleep function, right? Instead, the loop runs again, right? And so then it goes to sleep again. So this just keeps on going around forever, right? Notice that it's still not stopped, and if I try stopping it, it won't stop, right? But I can terminate it by typing in Control-C, right? Now, if I comment out the sig stop one and uncomment out the sig int one and save and recompile, seven. No, wait, this is, where did I, sorry. Right, so if I do that and run it, same thing, right? So the program is continuously sleeping for 1 second, right? I can stop it now, right? So now it's no longer responding to Control-Z. I can start it running again, put it into the foreground. But when I type Control-C, right, I can't kill it anymore, right? Which is why I said don't put in both, because if you can't stop it or kill it, and you're in Windows subsystem for Linux, you've only got the one window, right? You've only got the one terminal. So you can't open up another terminal and come in and kill the process that's running. But now I can kill the process that's running, right? So notice it's still running, right? And if I want to kill it now, you have to really kill it. So kill -9, so send the kill signal to it to remove it completely, right? And now it's gone, right? If you uncomment both, right, save and recompile, you won't be able to stop it from the command line. Okay? So you've been warned. If you're on a Mac, everything's fine, because you just open up another terminal, type PS, and look for the process that's running, and then kill the process. Yeah?
If you just, like, in Windows, close the Ubuntu.
Yeah, well, I mean, sure. Yeah, you can restart Ubuntu, but that's the same as restarting your system, right? Yeah. So generally, you should not handle the standard signals, except for the, well, you shouldn't handle the ones that let you stop a program, right? Because that really, that prevents the user of the program from stopping or killing your, terminating your program if they have to. Right. Okay, so instead of waiting, right, or running in a loop, right, so instead of waiting or polling, what you can do is you can install a signal handler to listen for the sig child signal. Right? Now you're still going to use wait PID to get the exit status of the child process. Right? So in signal 2, oh wait, sorry. Signal 2.c. Right? So this is a little bit more complicated now. So here's our handler. Right? And so the handler, if you look up signals, so if you Google signal GNU, G-N-U, you will come up with the code for this. It'll tell you exactly how, it'll give you an example of a standard signal handler that you can use to check if a child process is terminated. So the way this works is as follows. This will catch this will determine if any child process terminates. So if you have a program that launches many children, right, this will check whether any of them, right, any or all of them have terminated. Right? So it sits in an infinite loop here as well. Right? So while 1, and this is because it's listening for any arbitrary number of children. Right? You call wait PID. Right? You're going to use wait any. Right? So you check for any child process. Right? You're going to use W no hang so that the function returns immediately if there are no children who have stopped or terminated. Right? So if there's no children who have stopped or terminated, you immediately break out of the loop. Right? And so you exit the handler. Right? If the process ID that comes back is negative, some error has happened. Right? The errors that you can get from wait PID are that one of the errors is that there are actually no children, right, waiting. So that's a possibility. Otherwise, right, so if you do get back a process ID of a child that stopped or terminated, we're going to call some function here called notice termination. Right? You're going to pass in the ID and the status. Right? You don't have to use this function. Right? That's why the comment is here. right? So maybe you want to know what happened to the child process, right? So you want to know what its exit status is, right? And if you do, you can call a function of some kind, right? Up here, it just prints out that the child has exited with some status, right? And so now, down here in the main method, right? Before you launch the child, right, you're going to install the signal handler, right? So install the signal handler, listen for any child processes that have stopped, right, using that using that function. Then go ahead and do whatever you wanted to do, right? Now in the parent process is just going to sit in a loop forever, and it's going to do something, right? Do something can be interrupted by a child process stopping, right? So for example, right, so that child process sleeps for 5 seconds and then wakes up, right? So away you go, the parent's doing something, parent's doing something, parent's doing something, parent's doing something. Oh, there's the child, right? So it woke up. The termination, the notice termination function ran, and it printed out the child process exited with status 0. Then there seems to be some error saying there's no child processes, right? And then the parent keeps on going, right? And this will run forever until you kill it. The reason you get the error up here is because when the child process exits, the parent process has no child processes. So if you call wait PID and there are no child processes, that's when you get the error, right? So that's why we ended up here. Boop, boop. Here, right? Okay, so notice wait PID also uses this funny no mechanism, right, which I mentioned a few lectures ago, right? So in other words, wait PID sets the value of that variable when it encounters an error, right? This is the standard way that you're supposed to use no, right? So you're supposed to remember what the old value of no is, and then when you're done with it, you're supposed to set it back, right? Inside, you can check whether or not you can check the value of no, right? So here, when you get back a negative PID, right, a negative process ID, that indicates that an error has occurred, which means no has been set to some value. P error is a function that will print out what the error is looking at no, right? So in this case, it prints out that, right? So P error translates the error number and gives you back a string if it can, right? So that's what's happening there. Now, it turns out that what I just showed you is exactly what you're not supposed to do, right? So this is an example of what you should not do in a robust signal handler, right? But again, this goes beyond the scope of this course. So this moves into your operating systems course, right? The reason why you're not supposed to do this will be explained in your operating systems course. Sweet. All right. Any questions about today's lecture? Anybody? You want to wake them up? Because class is over. All right, so that's it for today. Wednesday will be the last class, I think. Will be the last lecture for this course. We'll wrap up, I guess. I don't know if I'm going to do any more process stuff or not. But for sure, I'll tell you what's on the exam on Wednesday.